Hi everyone, this is going to be our second lesson for 7.5, and we're going to compare features of exponential graphs with quadratic and linear graphs. And we're just going to learn a bit more about graphing exponential functions. So if we can recall from our last lesson for 7.5, an exponential function has the form of this for some real number b, where b is greater than 0. And here are some characteristics we talked about that we learned from that investigation, that the y-intercept is always 0, 1. If b is greater than 1, then the function is increasing, which means rapidly increases for positive x values, and the larger the base, the faster the growth. If the b value is a fraction, or between 0 and 1, which means it has to be a fraction or a decimal, then the function is decreasing. Rapidly decreases for negative x values, and the smaller the base, the faster they decay. There are no x-intercepts. The x-axis is a horizontal asymptote at y equals 0. The domain is x is any real number. And the range is y is any real number where y is greater than 0. And notice again, not greater than or equal to 0. It has to be greater than 0 because of our horizontal asymptote. So that's just me quickly just kind of reviewing what our investigation was. Now let's look at some transformations of exponential functions. So we're going to use the graph below to draw conclusions about the transformation effects of constants a and d on the y-intercept and the horizontal asymptote for each graph. So sorry, I'm just zooming out here so we can look at the equation. We're going to be looking at these transformations to our exponential function. So we have an a value and we have a d value. And we're just going to be noticing the patterns that are involved with them. So I'm going to zoom in a little bit on this graph. And I want to do that because I want you to see the equations in the note. But again, you have the note provided to you. So our dotted line here is y is equal to 2 to the power of x. Then if I put a value into the a spot here, a is in front of the b value here. So here I have 2 times 2 to the power of x. We notice that the graph seems a little bit steeper a little bit earlier on. And if we look at the graph at y equals 10, so a is equal to 10 here, times 2 to the power of x, this looks even steeper earlier on than the original graph of this dotted line. Also notice our y-intercepts. Of our original one, we have a y-intercept of 0, 1 here. Then when I have the a value of 2 here, my y-intercept becomes 2. And then when I have an a value of 10 here, my y-intercept becomes 10. So some things we can write here at the bottom. So for conclusions, when f at x is equal to a times b to the power of x, a transformation of a causes a stretch vertically by a factor of a. And this is for when a is greater than 1. Notice our y-intercept. Our y-intercept changes. I mean, if our y-intercept was 0, 1, and then we saw 0, 1 became 0, 2 when the a value was 2, and 0, 10 when the a value was 10. So the y-intercept is equal to 0, 1. But when we do that transformation, it becomes 0 and then a times whatever that value is of 1. So if this is 1 and a is 10, we get a y-intercept of 10. If this is 1, like our y-intercept of the original graph, if a is 2, then we get a y-intercept of 2. So that's how the y-intercept changes. Notice our asymptote here for these exponential functions is still y is equal to 0. So for the asymptote, y is equal to 0 still. So now we're going to look at what happens when we put the d value at the end here and see how that's going to transform our equation. And sorry, just to add here, I forgot the compression part, where this is going to be compressed vertically by a factor of a being less than 1. And this means more like a fraction. If we have like a fraction for the a value here, then we're going to have a vertical compression by that factor. Okay, let's look at the d value now. So here again we have our parent graph here is like y is equal to half to the power of x. We don't really see that here. Oh, sorry, we see that down here with the dotted line. So this is our y-intercept of 0, 1 here. And then notice the d value plus d. Notice with our other transformations, this is on the outside of the brackets, and it's not near the x value, so it's just on the outside. So notice when I change the d value, here it's 2, here it's 0, and then it's -2. My graph is really just shifting up and down. So a transformation of the letter d causes a vertical shift up when d is greater than 0, and then a vertical shift down when d is less than 0. So we have a negative number, our graph shifts downwards, and if d is a positive number, it shifts upwards. And this is the same for all the transformations we've done for vertical shifts up and down. Notice our y-intercept. Our y-intercept is 0 here, and our d value is 0. The y-intercept here is 3, and our d value is 2. Here we have -1, even though as our y-intercept, when our d value here is -2. So the y-intercept, oops, where did I put that? Y-intercept is 0, 1. And that's like our other y-intercepts. This is going to be 0 and then 1 plus d. So if d was 2 here, that's why we add 2 to get it to 3. And if it's 1 here, and then d is -2, then 1 minus 2 would be -1, which is how we get that y-intercept. So this is actually the same. Our d value just gets added to the y-intercept here. And our asymptote, notice when it's the d value is 0, it's at 0. Then when I shift it up to, my horizontal asymptote is also at, if I drew a little dotted line here, also at 2. And our asymptote at -2 here is also like this at -2. So for the asymptote, y is equal to d. So the horizontal asymptote is always equal to the d value that's here. Okay, and let's put this all together. So conclusion for f at x is equal to a times b to the power of x plus d. So combining a and d, what does this cause? Well, a gives us a vertical stretch or compression, and the d value gives us a vertical shift up or down depending on that d value. Again, negative is going downwards, positive is going upwards. Our y-intercept, how does that change? Well, the y-intercept, remember, for our original graph was always 0, 1, and then just like we did in the other transformations, this is going to change, it's going to become 0, and then the y value changes to a y plus d, meaning we're doing a vertical stretch or compression of the y value, and then I shift the y value up or down. Now it just so happens that for our y-intercept, the y value is usually 1. Sorry, it is 1, not usually 1. It is 1 for this exponential function, for our parent function. So if I have this, a times 1 is just a plus d. So these transformations will affect the y-intercept, where it's just going to be whatever the y value is, in this case 1, times it by a, which is just a, and then add d to that as well. Finally, for asymptote, what we learned before, our asymptote is always just equal to y is equal to d. So this is how the letter a and the letter d apply these transformations to these exponential functions. There is a horizontal shift left and right, but we don't have to learn that for this course. So let's get to some examples. Okay, so now we're going to look at some steps to sketching exponential functions, or at least identifying them. We're going to locate the y-intercept 0, a plus d. Remember, if the a value isn't shown, then the value of a is just 1. We're going to locate the asymptote, which is y is equal to the d value again. We're going to determine if the function is increasing or decreasing. And remember, that's if our b value is greater than 1 versus our b value being a fraction or a decimal. And we're going to use b to estimate how rapidly the function increases or decreases. So first we're just going to do some matching. Like here's the equation. We're going to match it to the graphs that are here, a, b, c, and d. So first ones I would look for is this one and this one, because they don't really have a d value here. This is plus 3 and minus 3. So I should expect there to be no really shifting up and down. So looking over here, I see B and C have not been shifted up or down because they have a horizontal asymptote of 0. I also notice my B value here, B is half, and then here the B value is 2. So if the B value is half, that tells me I have a decreasing. This is for decreasing. Let me go to a line here, so these are decreasing. And increasing is when the B value is greater than 1. So with the horizontal asymptote being 0 for B and C, and one's going down and one's going up, I'm going to say that these two, either one of these has to be and one of these have to be C. Since the C equation here, this line, is decreasing, I know this is going to be C. And since this one is increasing with a horizontal asymptote of 0, then I know this is going to be B. I can also check the y-intercept, because remember my y-intercept is always 0, 1. And if there's an a value, I multiply the y-intercept by a. So this would be 2 for my y-intercept, and this would be 3 for my y-intercept. So for equation B, I can see a y-intercept of 2. For my equation C here, I can see a y-intercept of 3. So that tells me that these are the correct equations here. So that leaves A and D there left over. So we can look at the y-intercept, we can look at the A or the B value. Again, B is 2 here, which means it should be increasing. And C here, B here is half, so it should be decreasing. Also, we have a vertical shift of 3. So usually my y-intercept's at 0, 1, and I've moved up 1, 2, 3, 4. 1, 2, 3, 4. And, oh yeah, because I have an A value of 2 here. Because remember, it should be A plus D. So if this is 2 times 1 plus 3 will give me 0, 5. This should be 0, comma that. And then for the D value, it's A times 3 minus 3, which would be 0, which is why I have a y-intercept here of 0. So this is going to be A, and this is going to be D. So the things that kind of helped me figure this out were, first off, the B value to see if it's increasing or decreasing. Then I can check my y-intercept with 0, comma A plus D. Or I can just do the vertical shifting up and down, and I can double check too. But I have to remember the A value does stretch or compress that, that y-intercept as well. So that's how we do example 1. Now if I went a little bit too quick here, please let me know, and then we can go over this a little bit more if you want to. I might have rushed through it too much. So yeah, just let me know, please. So example 2 is we're going to sketch this graph and this graph on the same set of axes. So we have y equals 3 to the power of x plus 1, and then f at x is equal to 2 times 1 over 4 to the power of x minus 3. All right, so let's start with our y-intercept, because that's usually a good indicator to help us graph this equation. So remember, our y-intercept is 0, a plus d. Because remember, the y-intercept is 0 and 1, so I could put a multiply by 1 here, but a times 1 is just a. So if a here is just 1, because remember, the a value is in brackets in front of this number. It's our b value that's 3 here. And then our d value is 1. Well, our y-intercept is going to be 0, 2. And then our asymptote, our horizontal one, is y is equal to d, and we said our d value is 1 here, so our asymptote will be at y equals 1. And then we also know our b value is equal to 3, so therefore it has to open, or has to be increasing, it has to be going upwards. So let's put these points on our graph. Well, I know I have a y-intercept at 0, 2, and I know I'm going to have a horizontal asymptote at y equals 1. So I'm going to put y equals 1 here, and I'm just going to put a dotted line to help me remember that there is a horizontal asymptote here. And then you know it's going to be increasing, and you might be wondering, well, how do I know what's going to go up to towards next? Well, worst case, when we have to graph anything, we can just make a table of values. So what if I made the x value equal to 1? Well, if x is equal to 1, we get y is equal to 3 to the power of 1 plus 1. 3 to the power of 1 is 3, plus 1 will give me 4. So I know when x equals 1, y will give me 4. And if I did this again for x equals 2, 2, 4, 6, 8, I would know that at 2, it's actually going to equal 10, because 3 to the power of 2 is 9, plus 1 is 10. So then I can make these points, and I know that I have a horizontal asymptote there, so it's not going to touch that line, and it'll just move upwards like this. So that's how I know I can predict what my graph is going to look like there. Now, on the same axis, we're going to do this equation, but we're always going to do the same thing. We look for the y-intercept, which is, again, a plus d. In this case, a is 2 plus negative 3. So that's going to give me 0, and then 2 plus negative 3 is negative 1. So for my second graph, I'm going to have a horizontal asymptote at negative 1. Oh, sorry, a y-intercept at negative 1. And then the asymptote is y equals d, which is y is equal to negative 3. So I'm going to have a horizontal asymptote at negative 3, like this. So again, we get to this point where you know the asymptote here, and you know the y-intercept, but you don't know what it's going to be before or after. So again, I'm just going to pick an x value, like I'm using a table of values. Just use x is equal to negative 1 here, because I want to know what's happening here. I know it's got to go downwards. Again, because our b value is a fraction, therefore it has to open downwards. So I'm going to pick a negative number. So if I have y is equal to 2 to the power of 1 over 4 to the power of negative 1 minus 3. I have a negative exponent here. This is just going to make me flip this. So it's 4 to the power of 1 minus 3, which is 8 minus 3, which is equal to 5. So I have a point at negative 1 and 5. So at negative 1, I'm going to be at 5, which is like right here. Just making sure I did that correctly. So I know it's going to be going like this. I know it's never going to touch that negative 3 as that asymptote. So that's how we can sketch our graphs for these transformations based on the equation. Okay, looking at differences in exponential functions, meaning if we have a table of values, if the first differences are equal, we learned the function is linear. That's way back in grade 9. If the second differences are equal, then the function is quadratic, which we learned in grade 10. Well, what about exponential functions? Well, let's look at this table of values here. If I find the first differences, we have 5 minus 4 is equal to 1. I'm very sorry, that's a little sloppy. 5 minus 4 is equal to 1. 7 minus 5 is equal to 2. 11 minus 7 is equal to 4. 19 minus 11 is equal to 8. 35 minus 19, I can do in my head, but I'm going to get it wrong. So I'm going to awkwardly look for a calculator. 16. Oops, sorry about that. So I just do my first difference, subtracting the lower y value from the higher one, and I get these numbers. If I were to now find the second differences to check if it's quadratic, 2 minus 1 is equal to 1, 4 minus 2 is equal to 2, 8 minus 4 is equal to 4, 16 minus 8 is equal to 8. So this is not quadratic either. But if I look at the first differences and I do the ratio of them, so normally for our differences we subtract these, but now if I were to get these, I can get the lower one divided by the upper one. So 2 divided by 1, I get 2. If I get 4 divided by 2, I get 2. And you're starting to see the pattern. 8 divided by 2, oops, by 4, gives me 2. Like I always say, you're getting the pattern, and then I make a mistake. 8 divided by 4 is equal to 2. 16 divided by 8 is equal to 2. So compare the ratio of the differences with the base b of the exponential function. What do you notice? We notice the ratios are the same. So when given a table, we can know it's an exponential function if we find the first differences and then we find the ratio between those first differences. And it just so happens it also works out for these second differences. But easiest just to do with the first differences, you can save yourself a bit of time. So that's how we can use a difference table or table of values to help us figure out what type of equation it's going to be. Alright, so this next example just says the data for the growth of a watermelon was collected and recorded below. Classify the data as linear, quadratic, or exponential. Give reasons for your answer. So if we're given the table of values like we just learned, I can find the first differences. So 18 minus 10, which is equal to 8. 34 minus 18 is equal to 16. 66 minus 34 is equal to 32. Oh boy, running out of space. 130 minus 66 is equal to 64. And you can kind of guess the pattern here. We have 258 minus 130, which is equal to 128. So if we did first differences, 16 minus 8 is 8, 32 minus 16 is 16, 64 minus 32 is 32. So first differences, it's they're not the same, so it's not going to be linear. So let's cross that out. Even if I did quadratic, it's still not going to be, the second difference will not be the same either. So I'm just going to do our exponential where we did the first differences. I'm just going to check the ratio. 16 divided by 8 is equal to 2. 32 divided by 16 is equal to 2. 64 divided by 32 is equal to 2. And 128 divided by 64 is also equal to 2. So just knowing the ratio of the first differences is equal to the same number, they're all constant at 2, we can say this is, therefore, exponential function because the ratio of the first differences is constant. So with table of values, linear relations are first differences, quadratic is second differences, and exponential is the ratio dividing the first differences. And if they're constant, then that's got to be an exponential function. So summarizing, linear, quadratic, and exponential functions. Our general equation for linear functions is, it should hopefully be ingrained in your memory, y equals mx plus b. For our quadratic equation, we're just going to use the standard form, ax squared plus bx plus c is equal to 0. And then for an exponential function, we learned y is equal to b to the power of x. When we're trying to figure out something, a table of values for a linear function, we look for the first differences. That's an r there. First differences are constant. We found for table values for quadratic functions, we have the second differences are constant. And we know for exponential functions now that first difference ratios and underlying ratios are constant. And for the last bit, I just kind of filled it in to save some time of writing. So our graph of a linear relation, remember, is just a straight line. A graph of a quadratic function is a parabola. And the graph of an exponential function should always be increasing, or alternatively, if it was decreasing down like this. And they can open up. This could be moving downwards. This could be opening downwards. I just gave you the basic parent functions for each of these graphs. For a y-intercept, it's for a linear function, it's always the b value in y equals mx plus b. If I have a quadratic function, it could be in different forms. Could be in remember, it could be in vertex form or factored form. We just have to set x equal to 0 to find the y-intercept. And to find the y-intercept for an exponential function, for the parent function, it's always 0, 1. But then if it changes, it's going to be 0, whatever the a value is, plus the d value. The domain for all of these is x is any real number, meaning they always go off in any x direction, in the negative or in the positive, forever. So any x value exists here. There's no vertical asymptotes. And the range for a linear function is y is any real number, because again, any y value exists if I extend these lines in either direction. The range for a quadratic function is y is any real number, but y is either greater than or equal to the vertex, or y is less than or equal to the vertex, depending on the opening. So it depends on if the equation opens up or down. And for this range for our exponential function, y is any real number, where y has to be greater than the horizontal asymptote. So y is greater than some d value. So that's kind of a summary of all of our functions. Our homework is here, and thank you very much for your time.